All right, so today we want to finish off talking about debugging. And then turn our attention to Git internals, with the proviso that we're not going to really look at all the Git internals. That would involve looking at all the Git source code and all that sort of thing. So we don't really have time for that. This is really sort of a subset. Enough to get you going. And we're discussing this subset more so that you have an understanding of Git's strengths and limitations, as opposed to intending you to actually work on Git internally, that sort of thing. But first, debugging. So last time we were doing sort of a brief tour of GDB. Commands. Again, with the idea of understanding its strengths and limitations. And we figured out how to start a program, right? With the proviso that it could be that you don't start the program under GDB, you can attach to a program as well. It could be either one. Now, you're sitting here, either started or attached to a program here. You have the GDB prompt. What are the sorts of things you can do? Well, first off, you can sort of give up, right? It's always important when you get into a system to figure out, how can I get out of this? If you've attached to a program, you can just say detach. What this tells GDB is, I don't want you to be controlling this other program. I want you to sort of give up and let the program run free, as if it had never been attached to in the first place, right? This means, in effect, give up control. And the process that you're debugging is no longer being debugged by GDB or by anybody else. You might wonder, what would happen if two GDB sessions try to attach to the same program? You've got two different people debugging the same program. What do you think should happen then? Two people debugging the same program. Any thoughts? Yes. Right. It's sort of a deadly embrace. Well, that's not the right phrase, right? It won't run unless both of them say run, that sort of thing. But what if one wants the program to run this way, one wants it to run that way? I don't see how it could work. And if you actually try to do it, GDB will say, I can't do it, right? Because the operating system won't let you attach to a program that somebody else is attached to. There can only be one sort of puppet master behind a program. You can't have two. All right, so another thing you can do, of course, is you can exit, right? This tells GDB to exit if it's started up by attaching to an existing program. In effect, you detach it. If you start it up by, you have some other program sort of started up by GDB itself, GDB will say, hey, wait a second, you want me to exit? What about this program that's running? And you can then say, yeah, I want both of you programs to exit, that sort of thing. All right, so once you've sort of started your program, and if you'll recall from last time, there was the run command. Then at that point, the underlying program is running, and in some sense, GDB isn't, right? Because if you're just running at the terminal, at this point, the underlying program takes over, right? And if at this point you type into your terminal, you're typing to that underlying program, not to GDB. GDB is sort of in some sense suspended, waiting for something to happen. In some sense, it's like the shell. When you run a program from the shell, then that program's running, not the shell. The shell just waits for the program to exit. But GDB is a bit more complicated than the shell when it comes to sort of maintaining control over the terminal, in the sense that if this happens and you type Control-C, right? Ordinarily, if it were the shell, Control-C just exits the program. But with GDB, Control-C, in effect, suspends the program and gets GDB back in control, right? So after you've typed Control-C, you'll get another GDB prompt. At this point, GDB is talking to your terminal, and the underlying program is not running. It's suspended. It's not exited. Its state is frozen, but GDB is now in charge, and you can now use GDB to examine the state of your program. All right. So what sort of things that can you do at this point? Right. At this point, we are examining program state. The program is stopped or suspended. So suspended program state. And the classic thing that you can do with a program that has stopped and wants you to look at it is get a backtrace. There's a very commonly executed command, BT in GDB, which means get a backtrace. And the simplest way of thinking about a backtrace is that the way software operates at the lowest level, which you'll see in CS33 and that sort of thing, is that there's a stack, a program stack. And when your program starts up, here's mains variables. All the local variables in your main function are residing in this part of memory. Every time you call a function, say main calls f, it pushes this stuff onto the stack. And if f calls g, the stack grows this way. There's a stack pointer that's part of the machine. On the x86-64, it's the RSP pointer. And this part is unused. When you type Control-C, here's the stack. What GDB will do is it will say, oh, you're in the middle of G, right? And so it will print out G, right? And likely G's arguments. And maybe the machine address, because it's ready for you to debug at a low level. And then it will print out F and F's arguments, and then main and main's arguments, and so forth and so on. Well, actually, this is when it stops, because we've reached the end of the stack. It could be that your program is fairly deeply nested. You've written some beautiful recursive program, and the stack is quite large. You know, it's got 100 entries in it, or 1,000 or something like that. In that case, GDB will start printing out a lot of stuff. At some point, it'll say, you sure you want to see this? And all that sort of thing. But you'll see a big stack backtrace. What can you learn from the backtrace? Well, you can learn what the program was doing when you typed Control-C, right? In some sense, this will let you get a tiny little snapshot into the execution of your program, all right? And that can be useful at times. But there are other reasons you might get a backtrace. So, for example, suppose you run the program, but instead of you typing Control-C, something else happens. The program crashes, right? So dereference a null pointer, say. There's a bug. I'm trying to write the word deref here. We'll get there. Right? In that case, your program will crash, but if it were the shell, you'd return back to the shell. All traces of the program have been lost. But when the program crashes, again, it's just suspended, right? So you've got a suspended program and you can get a backtrace, and the backtrace will tell you the exact moment where the crash occurred. And that can be very helpful, right? You'll see that somewhere in here, this machine address, if you've compiled with -G, will have a source code line number, and you can go see the source code line number and kind of figure out what caused the crash. Or maybe it's not G's fault, it's F's fault, but you'll see the same thing here. This information is present in the executable, assuming you compiled with GCC -G something, say G3, that sort of thing. The -G option tells GCC to put into the executable the source code information, or at least enough of it, so that GDB can print out useful stuff rather than just machine level stuff. All right. Now, once you're in here, this program isn't running, right? And you can now figure out maybe more details about why it crashed by printing out the values of variables. And GDB has a print command, which most people just type P, that will let you do that. So for example, if this source code line number says something like this, P, X arrow Y arrow Z equals 27, and it crashes due to a null pointer, well, you can print out the value of X, right? By saying P space X return, and that gives you the value of that local variable. You can put an expression here too. You can say Px arrow Y, right? And what GDB is smart enough to do is it'll say, oh, I'll look up the value of X, which I know because I've got source code information. I know it's stored at this place in the stack. And then I'll look to see what that points to, because the information about the data structures has also been put into the executable by -G. Fine. What else can you do? Well, you can tell GDB, please don't print it out in decimal. Please print it out in hexadecimal with something like this. This little modifier here says print it out in hexadecimal rather than decimal. And there's lots of other modifiers. The print command, in some sense, is the most complicated command in GDB because people have various preferences as to how they want to print things. You can also, instead of printing at the source code level, right, which is the way most people debug, if you need to sort of figure out what happened at the lower level, you can print things out at the machine code level. So you can say something like this. This says print the value of the register RAX on the current machine. The RAX register is the register used to store return values. If you know that, you can see what the most recent function returned and that sort of thing. All right. If you want to see all the registers, there is a whole set of commands under the info brand, and info registers will print out all the registers at once, well, at least all the commonly used registers. Most machines these days have so many registers you don't want to actually see them all, but you'll see the most important ones this way. Now, so far, what we're doing here is we're just examining the state. But the print command, which in some sense is a little bit of misnomer, can do more than just look at the current state of the debugged program. It can also change the state of the current program. So what you can do is say something like this, Px equals 0. All right? So the argument of the print command can be an arbitrary C expression, and that expression is executed in order to figure out the value that you want to print. This command is going to print 0, but it's also going to assign 0 to X while it's at it. Right? So what we've done here, presumably X is a local variable, we've told GDB, please go change the value of that variable in the debugged program. That means if the variable stored into the stack, whatever value X used to have, GDB will go and modify the debugged program stack and make it 0. The debug program isn't running, so it's not going to know what's happening until it starts running again. And this control extends not only to the memory of the debugged program, it extends to the registers. So you can do something like this if you want. This sets the RAX register of the debugged program to be 19. Thus, we are now pretending that the last function returned 19 instead of whatever it actually returned. Right? So what's happening here is that in some sense, GDB is changing the debugged program as it runs. We're changing the debugged program dynamically. And in this case, just a little bit. It's as if somebody sort of stepped in and put in an X equals 0 statement into the program, and then let the program run as if nothing had happened. But you can do much more than that. You can do something like this. X equals, right? Or even better, something like this. Let's do this instead. This executes, I mean, this is a C expression. So it causes the debugged program to execute the equivalent of this expression, right? And then whatever that expression returns, getChar will return a number between -1 and 255. Then it'll assign that number to X and it'll print out the value of that number. But let's think of what's going on here in the debugged program. Assuming that here's what the debugged program looked like before we did this print. This is causing the debugged program itself to call its own getChar function and then return, right? So what's going to happen here is that temporarily, this unused stack area is going to be used because getChar has got to run, and it, needs some stack space to run, and getChar might call some other function like read or something like that, right? So there's going to be this level of activity in the stack of the user program, and the user program is going to be running perhaps for a while before it finally returns, right? When it returns, all this stuff is popped off the stack again. And then GDB sort of regains control and assigns the result to X. Right? So in some sense, what GDB can do is it can cause the debugged program to, at any point in time, to call any sort of code in that debugged program that GDB wants it to call. And that's a fairly powerful thing to do. Right? So for example, you could even do this. Exit 1. Right. You're causing the debugged program to call its own exit function. This will terminate the debugged program, right? So it's really a very powerful thing to do. Any questions about this ability? Yes. Yes, right. So if for example, this expression, either directly or indirectly dereferences a null pointer, then the executing program will, have this problem. And when this problem occurs, GDB automatically takes over. What it will do, by the way, is it'll say something like, well, when I was trying to print this out, it crashed. And instead of entering some sort of recursive debugging, we're trying to debug why getChar fails. It says, I give up. Let's just go back to right here and pretend that didn't happen. So it won't recurse in that sense, but it will take over control. And then you can try running something else with the understanding, though, that some side effects could have occurred here. It's not that you've recovered the state of the program before you call print. It's that the program is executed and it's done something, and now you can see what sort of mess you got yourself into. Question? By default, numbers are in decimal in GDB, just like they are in C. If you wanted it to be hex, you could say, you can use hex numbers in GDB as well. Okay, other questions about this ability to examine and modify the suspended program. Now, you can't do this stuff while the underlying program is running. That would, well, among other things, it would lead to all sorts of race conditions. You try to look up a variable at the same time it's being modified, that would be sort of a disaster. All right. Fine. So we've seen how to start and exit a program. We've seen how to print out stuff and change stuff. But there's another set of techniques that it's very important to understand when you're debugging any program, and certainly if you use GDB. And that's the following sort of idea. When you're using GDB or any debugger, as I mentioned last time, what you're really doing here is you're exploring a program execution history, right? So in fact, if I could rename GDB, I would call it the Program Execution History Explorer, right? Program Execution History Explorer. All right, well, that name's not gonna catch on, is it, right? But that's really what we're doing. And the problem is that a typical program will execute billions or trillions or even quadrillions of instructions. This execution history is really long. You don't want to look at every instruction your program executes if it's non-trivial. It's just too hard. It takes too much work. You don't have the time. So what we need is we need tools for examining this very long execution history without looking at each individual instruction or each individual line of source code, right? It's just not going to fly. So there are several sort of techniques for looking at that history efficiently. The most common one, and the most best understood and widely used, is the technique of breakpoints. And the basic idea is as follows. You know your program's going to start up, and it's going to do a bunch of initialization, and it's going to, I don't know, consult the web and all that sort of thing. But eventually, you'll get to the line of source code that you're actually worried about because you think it's buggy. You have good reason to think the bug is here, right? So what you want is when the execution gets to foo.c and maybe line, 2917, right? Here's where you want the execution to stop. Now, in principle, what you could do if you had superb timing is you could type run, and then you could wait until it gets just before this line of source code. Then you could type Control-C, right? But nobody has that kind of timing, right? At least I don't. And so there's a better way of doing it, which is before you run the program, right? You start up GDB. You get the prompt. But you're not running the program yet, so the program hasn't even started. You can set a breakpoint at the place that you're worried about, which is foo.c 29.7. And B, the breakpoints are so commonly done. There's a long command, but I always just type B, right? Foo.c 29.17. Or actually, more typically, I don't even type B. I let my IDE put in the breakpoint for me by pressing the appropriate keys in the source code, right? That's a very common approach as well, or using the mouse and that sort of thing. But at the lowest level, this is how it works. You tell GDB where you want the breakpoint, and then you start running the program, right? With the arguments X and Y. At this point, the program takes over. It runs at full speed, right? But the first time it executes machine code in this area, it stops, right? So it'll run for a while, and it may give you some output and all that sort of thing. Then you'll see a GDB prompt, and it'll say, breakpoint at foo.c line 2917. Now, this sort of thing is quite common, and you don't have to do it with just one breakpoint. You can have lots of different breakpoints in your programs. You can say before you start running, oh, also, if I ever get to, bar.c, or maybe actually more commonly than doing it this way, I say, I'm worried about the getChar function. So let's put a breakpoint on getChar. Right? You don't have to specify a source file and line number. You can just specify a function name, and it'll say, okay, whenever that function's called, I'll stop. Right? And so you can have a whole bunch of breakpoints in your program, and you can think of them as being lots of little fences in your program, such that whenever the program tries to jump over that fence, it stops and lets you get control. If you do this a lot, you'll have a lot of breakpoints, and you can keep track of them with the info break command. Right? This lists your current breakpoints. Because you may discover that you've put in too many breakpoints, and your program is just barely running. It runs for a little bit and then stops. You say, oh, I don't care about this breakpoint anymore. So you can delete breakpoints as well with the delete command. Delete 19. This deletes your 19th breakpoint and so forth and so on. All right, so this gives you a way of having GDB run to specific spots in your program, and then when it's reached a breakpoint, you can then start doing this sort of thing and examine more carefully what has gone wrong in this sort of troublesome area. Question? Oh, this deletes the 19th breakpoint, right? Yeah, the info break will list them out with, whenever you create a breakpoint, it'll give you, oh, you're creating the third breakpoint and all that sort of thing. And so this will let you sort of, do that. All right, so once you've stopped at a breakpoint and you want, okay, you say, okay, I now understand the situation now. I'd like the program to keep going. You can tell the program to keep going by telling it to continue. There's a continue command, which is abbreviated C. This means continue after a breakpoint. Right? And so then it will keep going until it hits the next breakpoint. Or if you're in a loop, maybe it'll hit the same breakpoint again, right? Breakpoints only talk about what does the underlying machine instruction pointer look like. And if you're in a loop, you keep executing that same loop over and over again, you'll hit the same breakpoint over and over again. It could be that you know that the bug is in, say, the 10th iteration of the loop. And so what you can do is you can type C, wait for the breakpoint C. You can type C 10 times in order to get to the 10th iteration where the buggy thing occurs. But if you want to save some time, you can do something like this. This means continue. And the next breakpoint, when I hit that, continue then just automatically. Don't stop. Just keep going. Do that 10 times and then stop. Right? So sometimes this can save you a lot of sort of typing C and return business. All right. Just why don't we talk about how this works, right? Because what I'm saying here is that the program runs at full speed under GDB control. And yet we have this ability to create breakpoints, which means the program is running at full speed, but when it hits one of these breakpoints, it immediately stops. How can GDB arrange for that to happen? Well, here's one way. It's not necessarily the only way, but it's one way. GDB before the program runs, or while the program is suspended, has the ability to reach in and change the program that's being run, change its memory. It can go in and change its memory, or it can change its registers and that sort of thing. So the way it creates a breakpoint is as follows. Here are all the instructions of your program. Right. These instructions live in memory somewhere as well. You know, the stack's here, the instructions here. It's all one big happy piece of memory. So somewhere in these instructions are the machine instructions to execute getChar, right? Here's the getChar machine instructions. They're right here. And GDB knows that they're right here because that's part of the debug information that it's told, you know, that's in the executable. The executable says getChar starts at this location and it goes on for these many bytes. Now, these are a bunch of, you know, this is machine code, and it could be quite complicated. But GDB has a simple way of putting a breakpoint on that particular machine code. All it needs to do is take the first byte of machine code here and remember what it is, but temporarily, it'll put some magic instruction here, like the df instruction. Don't quote me on this. There's some instruction here that if you try to execute this instruction, your program will reliably crash. Right? So the way it can create a breakpoint is it temporarily modifies your machine code so that it crashes. Well, that sounds pretty bad, but it's not bad. The reason it's not bad is that once your program has executed this bad instruction and it's crashed, GDB says, oh, now I can go change the instruction back to be whatever it was, right? Maybe it was an 01 or something. And then it gives you the prompt and say, okay, the breakpoint's been reached. Right? So because it can go and temporarily change the program that you're running, it can efficiently implement breakpoints. When the program runs, it runs at full speed. And it only stops because it executes a breakpoint instruction. Okay? That's an important sort of performance thing. It's not that GDB is interpreting your program. That would be slow. Then it would have to be decoding instructions and figuring out where all the registers are. It lets the program run at full speed, but it just tricks the program into being debuggable. Question? Yes. Oh, yeah, right. So absolutely right. It won't work to shift the instructions around because a lot of the code, it might have absolute jumps to this location. You're going to screw it up. So instead, it modifies the first byte of the machine code in place. GDB has its own memory, right? And so it remembers all the breakpoints, right? It has a breakpoint list somewhere. And so it knows every place that it wanted to put a breakpoint. In that list somewhere, it stores the proper value of the machine code, what it should have been. When the breakpoints hits, it goes and slaps it back in, right? Then when you say continue, what it does is it goes through this breakpoint list, modifies all the breakpoints to have the breakpoint instruction again, and then lets the program run. So it's constantly sort of modifying the program behind your back. You never see the modifications because whenever you see the program, it looks good, right? Yes. Oh, yeah. Your debugger has bugs. Oh, that's happened to me. Oh, it's not fun. It's not fun at all. If your debugger has bugs, right, like you'll tell it to print out the value of a variable in the debugged program. It prints the wrong value because the debugger is bugged. Or you tell it to go change something in the program. It changes the program in the wrong way. You are toast. You are totally toast, right? So there's a very high premium on GDB not having bugs. The people who maintain, you know, because GDB is like the low-level debugger. When your high-level debuggers screw up, you use GDB to debug them, right? When GDB screws up, what do? there's you write your own debugger and use it to debug GDB? What do you think people do? If GDB has a bug, how do you think people address that? You're the GDB maintainer. You've mistakenly introduced a bug into GDB. You want to figure out what went wrong. What do? Yes. Correct. But you use an old version of GDB, one without the bug, right? Then you'll be off to the races, right? Now, but suppose the bug that's in GDB is a very old bug. It's been there for ages. Now things get tricky. There are ways around that, but let's hope that it doesn't happen. And to be honest, I very rarely run into GDB bugs because people are very careful about updating. All right, so where were we? Breakpoints. Oh yes. So continue, right? So if we run through the commands that we have to control the execution of the program, right? So we had the run command, or R for short. We have the continue command, which means continue after a breakpoint. But there are some other commands that get used a lot. And in some sense, these are shorter versions of what we already have, right? So one of them is very simple, stepi. The stepi command executes a single machine instruction in the underlying machine and then stops again, right? So you can think of it as saying, sort of put a breakpoint on the very next instruction, right? And then run it. And of course, that instruction is going to immediately halt because you put a breakpoint there. But it's actually a little bit trickier than that. Because it could be that the very next instruction is a jump instruction or a call instruction. It's going to put the register, it's going to point somewhere else completely. So usually the way stepi works is the underlying hardware has a way of executing just a single step of an instruction and then crashing. The x86 does that, ARM has that, all that sort of thing. And GDB uses that special flag in the hardware to cause the underlying system to execute just one instruction and then immediately crash, returning control back to GDB. All right. There's a related function called step, which is actually more commonly used by most people programming, right? This means step over a single machine instruction. The step command means execute code until the source code line number changes, right? So this steps over a single source code line. And to some extent, GDB can implement step by executing lots of step i's. At each point, it figures out, hey, did the source code line number change? And if it didn't, it just does another step i. And it keeps doing that until finally we've executed the 10 machine instructions of this source code line and we've gotten to the next source code. Or maybe we've jumped to somewhere else because it was an if statement or something like that. But either way, it will stop and tell you, where we changed in the source code. Now, you have to be careful here, right? Because I've told you verbally the algorithm for how step works. And I've sort of implied that this is kind of the intent, right? The intent is we want to sort of, typically we're in like Emacs or Xcode or something, and we said, I just want it to go to the next line, and so execute enough code to get there. The problem is that optimizing compilers don't always generate code in the same order that you wrote it, right? So you can have a source code line that maps into machine code in unexpected ways, right? So you can write something like this, x equals y plus 1, and then z equals x minus 2 or something like that. But the machine code could do something like this, let's load a Y, or let's move long Y into EAX, right? So we're starting to execute this guy. But oh, now let's move long 2 into RBX. What we're now doing is we're executing code here because we're planning to do a subtraction, right? And then, okay, now let's move long 1 into RSI, right? All right, so in effect, this source code line matches these two machine code instructions. This source code line matches this machine instruction. If you execute a step command, it will execute a single machine instruction, say, oh, the source code line changed, and it'll put your cursor down to here. Then you'll say step again. It'll say execute another machine code and say, oh, we're back up to here. From your point of view, execution has gone backwards. You were here, you said step, and it said, okay, we're now here. That's what actually is happening at the lower level. GDB is faithfully reflecting to you how the execution has occurred, but it's counterintuitive. And it's counterintuitive because of the optimizations that the compiler has done, right? The order of execution of machine is not the same as the order that you see in the source code. So for this reason, if I'm doing low-level debugging and start getting confused, sometimes I will go back to this level and sort of, try to figure out what's going on. That reminds me, I should tell you about one other command that's very helpful. If you haven't taken CS33, you will, if you have taken it, you already know about this, but I'll mention it. The disassemble command, which is DISAS for short. The disassemble command tells GDB, please tell me the machine code that I'm executing. By default, it disassembles the function that you're currently in, right? So you'll get an output that's maybe 10 lines long if it's a short function, or 1,000 lines long if it's a complicated function. And it'll put a little arrow next to the instruction that you're about to execute next. And once you see this, if you know the machine, you can then use step I, figure out what's going on in that confusing situation, right? Normally, you shouldn't have to do this. When do I do it? Usually it's when I have a bad pointer or a bad subscript or something like that. It's screwed up my data structures, and it's caused my program to crash in the middle of some optimized code. And at that point, I really got to see, because I can't trust the variables anymore. The pointers have been messed up. So I really need to disassemble and figure things out, right? So for example, suppose you have a Stack Overflow. And G has a variable A that's an array. And the program has gone bad, and it's stomped over this array, and it keeps stomping. Of course, the array isn't really here. The array stopped here, but it thought the array kept going, and now it's stomped over F's local variables. It stomped on the return address. When G returns, it returns into goodness knows where. When that sort of thing happens, this can be a valuable way to figure out what went wrong. All right, what other things can you have? The next command is like step, except if you are about to call some other function, step will stop at the start of that function, right? Because the source code line has changed. Next ignores that and keeps running the function until it returns. So you can think of next as being like step, except sort of, execute function calls without stopping, subsidiary function calls. So if the next source code line calls the cosine function, then next we'll just let that cosine function run and return, and then it'll stop when you hit the next source code line, right? It won't stop you in the middle of the cosine function. All right. Here's another one. Fin, which is short for finish the currently executing function. In effect, it's like saying, please put a temporary breakpoint at the point of the caller. The guy who called this function, I want to know, I want to sort of catch execution when we return back to the caller. So it means finish the current function. Well, we'll do one more. There's an until command. You can say something like this, and this is also shorthand. It's U is short for it. You can say, execute until you reach this line of code, right? Or finish, whichever comes first, right? So in effect, it means put a temporary breakpoint somewhere at the current function and keep running till we hit that breakpoint, or if this function returns. Either way, then stop and then pretend there wasn't a breakpoint there, right? In some sense, all of these commands here are elaborations of the breakpoint command. So these are all be on steroids, right? You can understand mentally how any of these commands work by saying, oh, it's like you put in a breakpoint at just the right spot and all that sort of thing. But they're a lot more convenient than actually creating the breakpoints by hand. And to some extent, what's going on here is we're trying to have a really efficient way of saying very quickly where we want to be in this program execution history and then stop there because that's where we want to be. All right, any comments on these commands? Yes. Right, so U means, it's short for until. That means execute until we reach this location. So in some sense, you can specify anything here that you can issue to B, right? It kind of means put a temporary breakpoint here. And by temporary, I mean when we get here, the breakpoint goes away, right? So this will say, okay, run until we get there. But there's another way that we will have a temporary breakpoint, and that's if the current function returns, right? So the intent here, usually this is going to be some spot in your current function. And you've got a complicated function with nested loops and all that sort of thing. You don't want to have to sort of, single step through it. That's going to take too long. You just want to say, go to this line, keep executing this function until we get here and then stop. But if the function returns, then I want to stop right away. I want to see what's going on because I didn't expect it to return. So this U is kind of short for put temporary breakpoints in both ways out of here. Right? All right, other comments on these commands. Now, suppose, and this is a fairly common thing, you're debugging a program and the bug is somewhere around here. Okay. You're pretty sure it's here. The symptoms, it's dereferencing an null pointer, it's crashed, and it's somewhere around here. And you want to, in effect, put a magnifying glass over this part of your program execution history, right? Now, if you've put a breakpoint here, it's pretty easy to put a magnifying glass over this part of the history, right? Because you stick a breakpoint here, you run the program. Maybe the breakpoint is, right before a crash, and then you single step and you look at all the variables. You say, oh yes, that's fine. But what if the problem isn't here? What if the problem is over here? And in fact, to some extent, this is a more sort of common area that the problem has occurred, right? Because what's happened is you've dereferenced a null pointer. If you have a bad subscript or something, your program has crashed. You want to know what led up to the crash, right? You don't want to know what's going to happen after the crash. That's, the bug's already happened. You want to know what caused the bug. You want to reason backwards a little bit. The commands that I've given you here don't seem to help much, right? That is, Well, okay, if the bug is reproducible, then it's fine, right? The way you can explore just before your crash is type the run command again, right? Just type R. R means, oh, I give up, things are bad here. All right, I'll just run and try it again, right? And when I try it again, I'll get into this sensitive area. So maybe what I'll do is I'll put a breakpoint here, right? I'll say GDB, I'll tell GDB, put a breakpoint on foo.c 2905, right? 12 lines earlier, right? And then I'll run, right? I'll redo this entire execution history. It'll be billions of instructions, but that's okay. I got time, right? It's only going to take half a second. And then I'm back to here, and now I can explore the troublesome area. I think it's probably in those 12 lines. And then I can single step through those 12 lines and print stuff out and that sort of thing. So that's one way to operate. And it's actually can often work reasonably well if your program is small enough and that execution history is short enough. You can be off to the races doing it this way. So it'll work for student code. But it's gonna be problems if you have a big program, or maybe the bug is kind of hard to reproduce, right? It happens one time out of 10. You've attached to the program, and this is the 10th time when it fails. What are you going to do? That sort of thing. So it would be nice if there were a different way to sort of do this kind of retrospective analysis, right? Actually, there's another thing you can do. You can do this. A very common use of backtraces is to make inferences about what just happened, right? A backtrace, you can think of it as being a partial log of the recent history of your program. And that partial log will give you clues as to what went wrong before your program crashed. So that's also a very helpful thing to have. But it's not enough in general, okay? And what GDB has is a feature that tries to help you out here. So let's assume we're here and we can't restart the program for whatever reason. But what we can do is we can put a breakpoint 12 lines earlier. Say 2905, right? So that's 5 lines ago from where we crashed. And then execute the RC command. RC is short for reverse continue. And what this does is it tells GDB to run the program backwards, to undo the previous instruction, and then undo the instruction before that, and undo the instruction before that, and keep undoing until we get to any breakpoint. In this case, the breakpoint we hope we get to is that one. Now, this should give you a little bit of worry. At least it gave me a bit of worry, because there's no magic here. How does GDB do that? Yes.
I have actually a question, because what if like we allocate a pointer and then freed it, and now we're reverse continuing? We're trying to like free the null pointer, right?
Well, all right. So let's say between 2905 and 2915, you freed the pointer. Then when you reverse continue, you will unfree the object, right? So after the pointer's frees, it's invalid, right? It's just right. But you will reverse continue through the free. The object that had been given back into, the memory allocator is now, it plops back into the place. Its contents are valid. The pointer is now valid again. You are really sort of making time go backwards. All right. So how does it work? I'll give you a hint. Normally, this command doesn't work. If you want RC to work, you have to start up GDB with a special option that says, please run this program in a way that I can do a reverse continue. Yes. That's right. For this to work, GDB has to keep track of everything your program does in such a way that it can undo that, right? So if your program, for example, stores 27 into a piece of memory, what GDB will do is say, oh, let's write down somewhere into GDB's own memory what the old value of that variable was before we set it to 27. And it'll keep remembering what your program does. This can slow down execution immensely, right? Because now GDB, in effect, has to kind of single step through your program, keeping track of everything that it does in GDB's own memory. GDB's memory will now start bloating quite a bit, right? So that's the downside. But the upside is you get the RC command, right? So this is a trade-off. I normally don't run GDB in this mode, right? Because I find that my programs are big enough that RC is kind of slow. But in some cases, it can be a real win. Yes.
So under the hood, are there multiple history objects, or is there a single contiguous history object?
I think by default, it's just one. That's a good question. There might be a way of, in effect, doing a fork and all that sort of thing, which would let you have multiple histories. I offhand don't know about it. If there is, though, then of course that will be even more of a overhead, execution time overhead. But yeah, in principle, it should be doable. Yes.
You try to unfree memory, but you don't have enough memory to unfree, and you get a null point.
Oh, well, that's a good question. Here, that leads into sort of internal details about how the allocation and free works. Normally, when you free an object in memory, it's not like the memory is given back to the operating system. The current process, the current program sort of holds on to the memory. Your program can't access it, but it's really still available. Those kinds of unfrees can easily be done. The problem could be if, in some cases, it actually does give the memory back to the operating system. To do the unfree, it has to grab the memory back, and maybe the operating system, sorry, you're out, right? And in that case, I don't know what happens. It probably crashes or something. All right, other questions about reverse continue? Yes. Yes, and the reverse continue option does have sort of flags for that. For example, you can tell it, just keep track of the last, million instructions and don't bother keeping more than that, because, that bogs it down. And again, I'm not an expert in this area because I tend to not play with this stuff, but yeah, you can certainly play that sort of game. All right. So now I'm going to tell you a different kind of sort of fancier way of exploring execution history that I find works really well for me. And also a nice property is if you play your cards right, it's fast. Problem with reverse continue is it's going to slow things down. This approach also has that problems unless you know what you're doing, right? And this is the watch command. So the basic idea is pretty simple. You can specify any variable in your program, say watch XYZ, right? And in effect, you can think of this as being sort of like a breakpoint on data rather than a breakpoint on your program. A breakpoint on your program works by whenever the program counter hits a certain spot, GDB takes control, fine. A breakpoint on data works such that whenever your program modifies this variable, GDB takes control. Program suspends. You are now sort of, debugging the program, and you can try to figure out what happened. So, for example, suppose your program at some point does something like this, right? Star XYZ equals 19, right? Because XYZ is a pointer. And there's a whole bunch of stuff in here, right? Really complicated. And here you got a crash. And the reason it crashed is XYZ is an null pointer. right? What you'd like to do, I suppose, is figure out why this thing became null. And using the techniques we've already talked about, you can try to figure that out. That is, you can put a breakpoint maybe here, and then maybe here, rerun the program, or you can do a reverse continue and all that sort of thing. But there is a nicer way to do it, which is to say, okay, there's a whole bunch of code in here, a lot of recursive code, lots of methods. I don't know, and I have, the address of XYZ in here. And who knows who got a hold of that address and stored into the pointer. So what I'll do is I'll just say, tell me when XYZ's contents change, either directly, because there's a source code line in here that says XYZ equals null, or perhaps indirectly, because we did P equals address of XYZ, and somewhere else there was a star P equals null, right? Any way that XYZ can change, please stop the program then, right? And that way, instead of carefully stepping through all this stuff, I can just rerun the program. I'll do a watch, and then I'll say, GDB run, right? And it'll go through all of this, and it will tell me every time XYZ changes. And as long as the number of changes is relatively small, I can easily narrow down who changed it to be null. So you can put any expression here that you like, right? So you could do this if you like. What GDB will do is it will watch the value of this expression. Whenever the value of the expression changes, it stops. Okay. Notice that if XYZ is a pointer, you can say this. Right? That's the same thing as what I just wrote. This means whenever XYZ changes from being a null pointer to a non-null pointer, or changes from being a non-null pointer to a null pointer, then stop and let me know what happened, right? Because that's when the value of this expression changes. This is a very powerful technique to help you quickly narrow down where a bug occurred by thinking of an expression that's true when the bug has happened and is false otherwise, right? So you think of a nice little test case here, and then you just say, watch for that test case. And then GDB will quickly sort of, execute the program. And when the test case becomes true, it'll stop. And that's exactly where you want it to stop. Yes.
When XYZ is set equal something or star XYZ.
This talks about XYZ itself. It doesn't care where XYZ points to. I'm assuming we have this variable, right? So all this cares about is XYZ a null pointer, right? And so that'll control when a stop occurs. Oh, in this case, every time XYZ changes to be a different value, right? Then we'll stop. So if you change it from one pointer to another, you stop. Change it from pointer to null, you stop. Any change to XYZ will stop. Then we don't care. We just care about the value of this expression, not the value of wherever it points to. All right. So how can this happen efficiently? I said this was fast, by the way, right? How can this be fast? I mean, one way GDB could implement this is it could, in effect, single step through your program. And every time the program stops, it goes and looks at the value of this variable. And if it changes, then it sort of exposes to you. Otherwise, it does another single step. That's one way to implement watch. But that would be very slow, because in effect, GDB will have to look after every instruction, right? And so it'll be slower by a factor of 1,000 or something. Instead, what GDB will do here is it will rely on hardware support for watch points. The x86-64 allows a processor to specify up to 4 different locations to watch. The hardware will then, keep inspecting those pieces of memory. And whenever the hardware changes those memory, it will trap, okay? But that's done at full speed. As long as you're only watching up to 4 locations, it'll run as really fast. If you if you create lots and lots of watch points, then GDB says, all right, I guess I'll have to single step, right? So use this carefully and you'll be fine, right? If you say something like this, GDB only has to watch 2 locations, so you should be okay, right? But if you have some complicated expression or if you have a dozen watch points, then GDB will have to single step. So use watch points carefully, but when you do them, do use them right. They'll run really fast. All right. One more feature, and then we'll be done with debugging. This sort of relates to the idea of reverse execution, but perhaps a little bit sort of more efficiently. GDB has a checkpoint command. What checkpoint does is it saves the current state of your program, right? All of its memory, all of its registers, and all that sort of thing. It just squirrels them away somewhere into GDB's own memory, right? So in effect, what this means is we've now saved the state. And GDB will respond to this command with a message that says, oh, yeah, we've created checkpoint number 3, right? And then you can keep going, right? But you will have saved the state of your program, and then later on, you can restore it by issuing the restart command. This sort of thing, right? So what this does, it means it's sort of like the run command. Your program's starting up, except you're not starting up from scratch. You're starting up from where you created that checkpoint. If you're debugging a big, long-running program, it's so big that the RC approach isn't really going to work. This can greatly speed up your debugging speeds because you can create a checkpoint at a known good location in your program and then explore into a buggy area. All right, question. Oh, checkpoint gives you a label for every time you run the checkpoint command, it gives you a label. You just specify the label here. And at some point, you may have too many checkpoints. You can delete checkpoints, all that sort of thing. Question? Yes, absolutely. All right. Okay, well, way too long. Let's take a break, and we'll start up at a little bit past 1/4 past. All right, let's start up again. So we do have a little bit of time to talk about Git internals. And, again, this is just a small subsection of it. And in some sense, we're looking at the part of the Git internals that is easily exposed. There's a sort of a joke amongst the Git developers that has been told so often it's now part of the documentation, which is the distinction between the porcelain and the plumbing. So the idea here is that if you're a plumber and someone calls you to their house and says, my bathroom isn't working. There's this massive, the sink is plugged up and there's goop oozing up and all that sort of thing. As a plumber, you don't really care about the faucets or the sink, which is made of porcelain. That's not the problem. The problem is underneath the house. It's the pipes, right? And to some extent, what plumbers focus on, obviously, is the plumbing, right? Users don't see this stuff. But it's really how your bathroom works. And from a plumber's point of view, the porcelain is just decoration. And sure, if your sink is busted and there's a crack in the porcelain, they'll install a new sink and all that sort of thing. But that's kind of routine and it's not a big deal. It's sort of like, I don't know, shining the outside of your car as opposed to fixing the engine, right? So Git has kind of two levels of abstraction in terms of the Git commands that you can use from the shell. They're the plumbing commands that really have to do with the low-level sort of Git representation, the part that I'll be talking about today and probably, well, and next time. So there are the plumbing commands, and then there's the porcelain commands that are implemented in some sense atop the plumbing, right? They can operate by calling the plumbing commands. And most Git users, even at the shell level, only see the porcelain. Now, of course, this is not the only thing. Most Git users nowadays use GitHub, right? Or GitLab or something like that. So they use a web interface. These web interfaces will operate either by running porcelain commands, or for efficiency, they'll operate directly by using plumbing commands. But the users are going to live in this space, right? Most of the commands I'll talk about, even in today's lecture or the next lecture, are going to be also in this space. But occasionally, we will see some plumbing commands. And we'll also see something else. Not only the shell commands, the utilities that you use to deal with the plumbing, we're actually going to look at the file system representation or the file representation for the plumbing. Right? In a sense, these plumbing commands get their work done by changing files in your directory. If they couldn't do that, they couldn't do anything, right? Because they would just run, but there wouldn't be any change, right? So the state of Git has to be stored in files. And so we are going to look at that file representation kind of to understand how the plumbing works, and also to understand some of the strengths and weaknesses of Git, right? If you know the file representation, you're going to have a better intuition for why Git works the way it does and what things ought to be easy and what things are likely to be hard. And that's going to help you learn Git faster than if you had to learn it just from the user point of view. At least that's the goal. All right, so let's take a look. Actually, we're going to start by looking here. We'll look at the file representation. So I just logged into my directory here. And if we look in the source directory, here's the source code for Emacs, right? And I actually have an Emacs CS35L directory here, which I can do a git log. And if you'll recall from our git thing, oh my goodness, the files are very slow on this machine. Here we go, git log, right? So here is the state of the Emacs repository as of a few weeks ago, right? I haven't done a refresh since May 11, but that's all right. All right, so what I'm going to do now is I'm going to clone this. Git clone Emacs CS35L to Emacs. What should we do? Let's just call it May, right? Because it's still the month of May, right? So I've made a copy of one repository, and I'm now doing another. Now notice, by the way, it cloned the repository fairly quickly, but it's taking a while to do something called updating files, right? So what I had here was, I had an Emacs 35L subdirectory, right? I've created an Emacs May subdirectory, right? And underneath here, there's a whole bunch of source files. Plus, there's a very important subdirectory called git, right? Well, I guess I'll put the label here, why not? That has a whole bunch of stuff under it, okay? What those messages showed, and you could sort of see the timing on it, is that it created a subdirectory called Emacs May. It created a subdirectory called git for it. And this part was fast. It then said, okay, updating files. When it was updating files, it was creating all the source files. And there's a whole bunch of source files here, right? And this part was slower. Okay. Now, why is that? Well, let's see if we can figure it out a little bit by running this command, du emacs cs35l emacs May. Okay. The du command will print out the amount of disk space being used, du, right? Disk space usage, all right, of both of these directories, one original and one clone. And if we take a look at the disk usage, here's Emacs CS35L. Notice there's a whole bunch of space, right, in the git subdirectory of Emacs CS35L, 94512, if I'm not mistaken, 91452, right? So this is this many kibibytes, right? Actually, I guess it's like that, right? So 914512. Oh, so 914 megabytes roughly, right? And then if we keep looking at Emacs May's git subdirectory, notice it's 1244. Right? So this thing is 1244. It's only 1 megabyte roughly, right? And that's why copying this didn't take very long, right? It didn't use up very many bytes at all. Whereas copying all this stuff took a while because we had to actually create new source code files. There's sort of, there's a lot of files here, and it's a slow file system on CSNET, so that's why it took a while. Now, I think I've already mentioned why this was copied fast and these were copied slowly in a previous lecture, not last lecture, a couple weeks ago. So in some sense, I'm repeating myself. but in some sense, I'm asking you to remember, why was this clone so fast, at least cloning the repository? Because, you know, that repository stores the entire history of Emacs development all the way back to 1980 or something, right? That's a lot of data, right? The source code files are relatively small compared to that. So why could we copy the history faster than we could copy the source code file? Yes. That's right. Right. So almost all of this stuff is hard linked over to here. Not all of it. Some of it isn't. And what DU does is if it sees that it's already accounted for the disk usage up here, it says, well, I'm not going to count it twice. So this doesn't really count. If we, by the way, if we did it in the opposite order, if I asked DU, please count the disk space here and then here, it would say, well, this is big and this is small, right? Because it only counts the first occurrence that it finds. All right, well, let's take a look at this mysterious subdirectory in Emacs main. And I'm going to go straight, I mean, here's Emacs main, right? And it has a, you know, a whole bunch of stuff. Some of this is subdirectories, but the one I care about is the Git subdirectory. So let's look at that. And so what we're doing here is we're kind of looking at the top level of this history, right? Of this repository, I should say, and not history. So what's in it? Well, the easiest way to see what's in it is to kind of go look at it. Let's look in the branches directory. There's nothing there. Well, that's kind of useless, right? Well, I will tell you to some extent what this directory is for. It's empty now, and the reason it's empty is that it's obsolescent. There used to be a separate file in the branches directory for each branch that you create. And that file would record that branch, and a small amount of details is about that branch, right? This used to list branches. Your branches. And the directory is still kept there for the purpose of old copies of Git that you might want to run against this that don't understand the new stuff and all that sort of thing. But nowadays, it's not there at all. Branches are recorded somewhere else. I'm mentioning this partly to illustrate sort of a truism about software in general that we'll see more than one place in Git, which is we have a lot of backwards compatibility concerns. People don't like losing their source code. They don't like losing their repositories. They hate it. They will run away from you if your source code control system says, oh, you know what? We're switching to a new version of Git, and it won't work with your old repositories, right? Or it will create repositories that your old version of Git won't understand and will start printing out error messages. So the reason we're putting this in is purely for backwards compatibility with older Git versions. All right, well, let's try something else. Let's look at git config. That looks like it's going to be more interesting because it's a file and it's got some stuff in it. This tells you about this repository's configuration. And in some sense, it's a very important sort of file because Git uses it kind of first thing whenever it wants to know something about the file. So here's our configuration. And the configuration says things like, oh, which repository format are we using? Version 0. Well, that sounds pretty low. Let's see, the file mode is true, bear is false, all that sort of thing. These all have to do with fairly advanced Git features that you probably don't need to know about. Well, I'll tell you one of them. Bear. A bear repository is one that doesn't come with working files, right? So a bear repository would be one where this part Doesn't exist. The only reason you sort of keep around a bare repository is as, you know, something that you can clone from or that sort of thing. If you're only interested in history and not interested in development, then you would have a bare repository. If the repository is bare, Git won't sort of worry about the source files, won't sort of, you know, keep track of them or anything like that. And if it's not bare, which is in our case, and it's the normal case, it will start worrying about it. The remote section is more interesting. This tells Git where is the upstream or remote repository? Where have we cloned from, right? Where have we cloned from? At least when you start off, that's what it'll contain, right? And it will also say sort of where to fetch from. When we are trying to fetch updates from this remote repository, right? So the details here we'll get into later as to what that fetch sort of actually means, okay? And the other thing that is going to be in that configuration is information about our branches, right? In our case, right after a clone, you typically have just one branch. It's the branch that you've cloned from. Our case, the branch is master. And for each branch, it will list the remote that that branch came from. In this case, the origin remote, there's only one. And if we want to do a merge, where are we going to merge from? That sort of thing. This configuration file can get more complicated. So in Emacs, one of the first things you do just after you've cloned a repository, and in order to start working on it, you need to sort of modify the working files in the Git configuration to be sort of right for developing with Emacs. A lot of projects will have this. They'll say, okay, in order to start working on this project, do a Git clone and then run a bootstrap command. Or in this case, run the command autogen.sh. It's a shell command. We can look at it, right? So it's a bunch of comments and saying, all right, here's what to do just when you start up developing in a copy of Emacs. And it will start running Git, you know, has little shell functions and all that sort of thing. I'm not going to go into the details of how it works. I'm just going to run it. Whoops. Here we go. All right. And so it runs some automatic reconfiguration files, and it also does some Git configuration, right? Notice it's running the command git config transfer FSC key objects true, sort of a third of the way down, right? So you can modify this file directory, right? Just use Emacs or Nano or Vim or whatever your favorite editor is, right? You know, with the text editor, right? Or via a shell command, the git config command. It, in effect, acts as a little text editor for you. So you can say git config, the name of a variable, and then its value. Now, if we go look at our configuration file, it's going to be a little bit more complicated than what it started off to be, because we've now edited this Git configuration file in a way that's suitable for our project. So what have we changed? We've changed, say, the transfer sort of approach. This section of your Git configuration controls how much checking Git does when it copies repositories from upstream, or when it pushes sort of your changes upstream. Normally, Git does some checking, but not a lot. this FSCK objects thing says, oh, we want you to really do a nice file system check on every object. Don't trust the object data, actually check it. And then all of these diff things tell Git how to run git diff on various source code file types. If you're going to do a diff on elist files, here are the ways that you can find functions in those files, that sort of thing. So we've configured Git to be more the way that you like. This is actually a fairly small Git configuration file. Other projects will have really large ones because they're very sort of picky about how Git will work. If you mess up the Git configuration file, Git stops working. So you're going to have to be careful about what's in it. All right. What else have we got? cd.git. We have a file called description. This one is also somewhat obsolescent. We can take a look at it. It says, oh, well, you can edit this to be whatever you like, right? This file is not used by Git proper. It's used maybe by other applications, Git web, that sort of thing. And to some extent, it's somewhat obsolescent now. Most web-based applications use a README file or something like that instead, but it's there for backwards compatibility. All right, what's next? We have head. Right? So the head file lists, well, where you currently are, right? Right? It lists the current branch you're on. Possibly you're not on a branch at all, in which case head is just going to be a simple SHA1 checksum of wherever you happen to be. But the head file basically says, where are we right now? All right. We then have the hooks directory. All right, what's going on here? Hooks contains a bunch of scripts, plus sample scripts. All the file names ending in .sample are sample scripts. They're essentially ignored by Git. They're just there to give you a hint of what the corresponding hooks should look like. What are hooks? Well, let's take a look at the very first one, commit message. Right. So notice, this file is not something that Git maintained for us. This is a file is something that the Emacs developers put in here, right? For Emacs, these hooks were created by autogen.sh. More generally, if you're in some other project, maybe there'll be a bootstrap script, or maybe you'll just maintain the hooks by hand. Typically, it's done automatically, right? So you'll have a program that creates hooks. Hooks are scripts executed by Git at delicate points of operation, right? Git is trundling along, it's doing a clone, it's doing a checkout, you're doing a commit, whatever. But at some point, let's say you're doing a commit, Git will say, you know what? People are really picky oftentimes about what commit messages are to be allowed. Let's see if this project has a special rule for commit messages. And that special rule will be this script. And what this script is going to do is it's going to check to make sure when you do a commit, you use a commit message that the other developers in your project will understand. All right? So what does this thing do? It says, you know, take a look at what is in the commit message, and here's one thing it looks for, right? About a quarter of the way down. If it finds an unprintable character in the commit message, it says, nope, we're not going to allow that. We're going to exit with non-zero status. So if this commit message hook which is a shell script, exits with non-zero status. Git says, I'm sorry, your commit message is no good. I won't let you do the commit. Right? So it's a way of making sure that you don't commit with an empty commit message. You know, sometimes people get a little rushed and they say, oh, I'll just commit with nothing, right? And it says, no, 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 you really have to type something, be a good citizen and all that sort of thing. And, you know, it'll do some other checking to make sure you have proper URLs and all that sort of thing. So what sort of hooks do we have here? We have a hook for the commit message. We have a hook for pre-commit that can check the contents of the files as opposed to the contents of the commit message. We have a hook for pushing. If you're about to push a commit upstream, it does extra checks over what it would ordinarily do, and so forth and so on. And to some extent, you can think of these hooks as being kind of a self-defense mechanism for the developers. We are error-prone, we humans, and these commit messages, these hooks help us generate higher quality commits, which is going to be better for the project in the long run. All right, so that's the hooks. What's next is the file, the index. Let's look at it. Now, we haven't made any change to this particular repository. And as I mentioned to you when we talked about Git earlier, the index is your plan for the future, right? So we have no plans for the future. This is kind of the most dumbest and most boring index imaginable, right? Because we haven't done anything. It's a binary file, and it looks like this. All right, so what's really going on here is the index is a data structure that Git will fill in as you start doing commands like git add and that sort of thing. And this data structure will change, but from our point of view, it's just this big binary blob, right? And it gets updated to reflect future plans, but we kind of, at this point, don't really care. Well, you notice that, you know, already the index, it knows the names of our files. So it's keeping track of all of our files, but the information associated with each file right now says, we don't have any plans for this file. That sort of thing. All right, what's next? We have an info directory. And it has just one file that looks like this. And here, I hope it's fairly explanatory, right? This is a set of files that, that Git will kind of ignore. It won't worry about these files, right? And to some extent, this info file is separate from the git ignore file that I mentioned earlier. But it's one that's under Git control, whereas the git ignore file is sort of under your control. So we have two different files for those reasons. I don't use it much myself. What else have we got? We have logs. Right. So these files keep track of the changes that you've made to wherever your branches go. So let's take a look at logs head. You can think of logs/head as being the history of all the times that you've done a commit in this repository. Currently, our history is pretty simple. You know, all we did is we changed from nothing, that's all those zeros, right, to the current head commit, which is that second number, starts with 1C60, right? When we did the clone, we in effect went from nothing into that spot. And then this basically logs the fact that Eggert made the clone. He did it at that time of day. And then he did it by doing a clone. So it's a log of who did it, when they did it, and what sort of command they executed in order to do this. So you can think of this log file as being a meta history. It's a history of your changes to the repository. The repository is a history of your source code. The logs are a history of your changes to the repository. And that can be helpful when you mess up your repository and try to figure out why is it messed up and all that sort of thing. All right, what else have we got? We have objects. And this looks pretty boring, right? I mean, it's just a bunch of 2-letter directories, and there's actually a couple of extra ones at the end. In some sense, though, this boring directory is the most important part of the Git repository. It stores all of your Git objects. Git uses an object-oriented database to store the state of your repository. And each object is got a unique ID, which is that 40-digit hexadecimal number. And in order to keep the size of the object directory sane, Git uses subdirectories. So if we look, say, at ls-lff, right? There's one file here, ls-lfd, and so forth and so on, right? What's happening here is that the actual object is named ff7324, that sort of thing. We take the object name, we take the first 2 characters in the object name, 2 hexadecimal digit, and then we say, okay, we'll have a subdirectory that way, and then the rest of the name is sitting in a file. Originally, Git didn't have the subdirectories, but then the Git objects directory got too big and got too slow, so they split it off into 256 subdirectories, each having these 2 hexadecimal digit names. Inside these objects directory, you'll see the actual Git objects. Let's take a look at one of them. And it's more binary data. And to see what's in that binary data, we'll have to wait until next time.